Okay, so here is, let me write, just copy from here, so, so let's look at this situation. We have X is its distribution data, and X data has joint PDF f of X and theta. Okay, so theta is the parameter. Okay, so we assume that the random variable and theta, this is also capital theta, same. They have joint PDF of X theta, and so what we need here is marginals. We might need, I'm not saying definitely need that. So one of them is fxx, or sometimes they call it hx simply, and that is when we integrate theta out. And this depends on some domain. So let's just write, I'm not saying, well, we can write minus infinity, that's okay. We need this one. And also, the marginal for pi, for theta, which is this thing, pi theta is called prior distribution, or PDF of theta. Okay, so we have prior PDF of theta, and what we are looking for is this. We are looking for this posterior distribution of theta given X. So that's C of theta given X, that is small x, because we observe X. So this is what we need, and that is in fact f of x theta divided by that fx x, or I wrote hx for that. So you can either write hx or this. And sometimes I have written this, sometimes I have written this. Now let me see, in this formulation I have given that. So that's the same thing as this. Okay, and most often we really don't need this thing. Most often we really don't need this. And this also, this guy here is in fact h given theta pi theta. And that is where this comes into the picture. That is where the prior comes into the picture, this thing comes into the picture. Okay, so our job is let me erase this thing. So we choose data, pipe data. And that's observing X. Then what? Then use down the data. Okay. So that's let's say 1, 2. We choose what we have. We're given H0 and H1. We compute P of H0 given observed data and the P of H1 given again observed data using C. And the third one is just compare those two. Well, I have given you like a table which that's kind of different. Now in this, say this method, say, I don't want to say method, but in this one, it's just your call. So when you look at these two, most often if this is larger than this, so which means the ratio is bigger than 1, then you say, okay, we have enough evidence. And so, or you might say, okay, it has to be twice as big, say. So this has to be twice as big as this one to give you enough confidence that H0 is, or you accept H0. And all of this is based on observed data and this choice that you make at the beginning. So that's that makes this so, I don't know how to say that, it's quite different from the frequentist approach, which is just one thing. you find, say, the p-value, and based on the p-value, you decide. It's more flexible in a sense, and some people might say, okay, because of being so flexible, it's not good because you have either been yes or no. But well, this is the world of probability, and probability, in fact, means you have something between 0 and 1. It is not just 0 or 1. It can be anything between 0 and 1. But anyways, that is your choice. At some point you might stick with the other one, which I didn't go through that. That's okay, but you can read it. It's not that hard. It's very simple. Or you can stick with something else like the confidence intervals. So let me do 2 problems here, and then okay, so now let me write down some general forms. So one is when we have well, let's say we have normal situation. This x is a normal, theta and sigma 1 squared, which means we know sigma 1. So that's something you might say, how do we know that? And then we have theta, and this is in fact say capital theta, let's say. Oh, this is much better. Okay, so this is capital theta. And that's also normal. Well, let's say mu and sigma 2 squared. Now, if I do that, so this will be, so this gives me pi theta. And remember that pi theta will be something like 1 over square root of 2 pi sigma 2 e to power minus, say, theta minus mu squared over 2 sigma squared, something like that. And in fact, sigma 2 squared. So that gives me pi theta. And also for the other one, except here we have x minus theta on top. And this gives me 2 things. First of all, it gives me fxx. And then also, in fact, this gives so, well, I'm not going to write this thing, but which is marginal distribution of x is normal, in fact, with mu, and I can remember sigma 1 squared plus sigma 2 squared. So by using, those formulas, and I have given this as like a small theorem in those notes, so you can look at the notes. And well, also the more important is xc. So xc theta given x, that also gives me this, and this is in fact theta given x will be normal And yeah, it is like a large formula, and that is x sigma 2 squared, x sigma 2 squared plus mu sigma 1 squared over sigma 1 squared, sigma 2 squared. And its variance will be sigma 1 squared, sigma 2 squared over sigma 1 squared plus sigma 2 squared. And you can see that it depends on the observed x. That's the observed x. So when we observe x, that is in fact the distribution of xc. Now, let me give you an example, and this example should clarify what this thing is. Well, let me find that example here. So let me erase this and normal example for normal. Example. So this is a simple example, maybe just 2 lines. So let's say x is normal. So in this example, I assume that x is normal with theta and 100 as. Usually you choose something which is a square number for sigma because the sigma squared. And you choose, let's say this theta itself is normal. And I chose 100 and 900. Okay, so this gives me marginal. So marginal distribution of x is normal, remember, and with mu being this thing, and its variance is this one plus this one, so it is 100 plus 900. So basically it is normal, 100 and 1000. And posterior will be distribution of theta given x, that is theta given x. It is, remember, the formula was normal. If you calculate that, I have calculated this in the notes, and that would be 0.9x and plus 10 and 9. Okay, using those formulas, we have this. So that's it. So that was the example. Now, using this example, I also give you another example as testing hypothesis. So let me write that example here for you. Okay, so this is in fact can be a real life example, normal, and test of hypothesis. So let me this. So so let's say that someone has diabetes. So these people, they check blood sugar a few times a day, and one probably is in the morning when they wake up, and then after they eat breakfast. They say you check it 2 hours after breakfast. That's when the sugar from the breakfast is like in your bloodstream, and they want to see how elevated that sugar is, because it has to be absorbed, I guess, and if not, then it shows when you check it. Now, let's say that X is blood sugar level after breakfast, back 2 hours. They say. So we say that X, let's say it is normal. Well, this doesn't mean it is normal, but let's say it is normal with some theta and 100 as sigma. Now this sigma makes sense, because I know that this is some number which is around, say, 100 itself. And this being 100, it means that sigma is 10. So it's not that wrong, I say. I'm not wrong, I mean, it makes sense that this one to be 100. Because then sigma is square root of this, that is 10. And this one is 100, so we assume that theta is also normal. Now this time we say, okay, since we basically know that this is around 100, should be around 100, so we assume that theta is 100, and with 900 as sigma, this is like 30 squared, right? So that is sigma is 30, and again that also makes sense. So between, if it is 100, then 130 and 70, and that makes sense. So this is my assumption. These are the assumptions. And what is this one? This is in fact gives me the prime. This gives me pi theta. Prime. Okay. So this is the prior. This one is assumption. Even if you're doing the other method, if you're using frequentist method, then you have to make some assumption on the distribution of whatever you're studying. But in this situation, we make an assumption on parameter theta. So that's our assumption or belief that theta has normal distribution with its mu being 100, which is in fact this, right? So now we want to find both posterior distribution for x and marginal distribution for x and the posterior distribution for theta. So let's find them. I mean, we already did it in the other examples. So from previous example, we found, let's say from previous example, we found that x is 11000, I guess, if I remember correctly. And we found that it, what did I find? Yeah. And also we found the posterior distribution for theta. X, no, this is not X, that's marginal X. So that's right. I could have written X, that's okay, but anyway. 1000. But that's in fact X itself. That's okay. And also, I found that theta was given X was normal, remember, and 0.9x plus 10 and 90. Okay, now hypothesis. Well, hypothesis is this. So you check your blood sugar and you see that it is like 110. And you say, I think that's like the mean. So you just said, I think that's the mean, which is in fact theta. So you say that H0 is theta is less than equal to 110, and H1 is that theta is bigger than 110. This thing resembles the hypothesis test using frequentist method. So in that method or in problems like that, you have things like this. So sometimes you might say no, it's usually equal. In fact, it's either equal to this and not equal to this, or equal to this and bigger than this, or something like that. But here we can do that. So the H0 is that theta is less than or equal to 110. The other one is the theta bigger than 110. So this is in fact this x, because we observed x, right? We observed x. So what do we observe? We observed the x is like 110, something like that. So that was blood sugar. So your blood sugar was 110. So this is my x. X. Okay. So you observe that, and then based on your observation, you say, I think that theta is also around 110. Or let's say you want to see which one makes more sense. So your null hypothesis, H0 null hypothesis, is that this mean of the blood sugar is less than 110, and H1 is that it's bigger than 110. Well, this might be crucial for diabetes patient, because if it is like above something, then you have to take some medication. If it is not above that, and if it is less than that, then okay, then doctor might say, okay, no, you don't need medication, and perhaps with like some diet you can bring that down. So that's crucial in many senses, not just for the patient, also you have to pay for that medication. So let's say, so this is what we observed, and based on this observation we made these two, say, hypothesis. Okay, now we have to find the P of H0, so let me erase this thing, because I know H0, H1, what they are. So we, first of all, based on this observation, what is theta given x? So theta given x is 10 will be normal, and that is oh sorry, x was 110, not 10, 110. So 110, that's 99 plus 10, that's 109, and 90. Is it what I have here? So, and so that is in fact a posterior distribution, and so we want to find P of H0 given that my observation was 110, and the other one H1 given the observation was 110. Now this is what? Since these are complements, if I find this one is 1 minus that. Okay. If it's not the complement, then you have to find them separately. But in this situation, that's okay. So this is in fact using what was theta H0? It was theta less than, so that's in fact P of, say, theta less than equal to 110. So I have to find I have to use this thing, right? I have to use this using this. I'm using this. Remember the CDF of standard normal distribution, that capital phi. So I need capital phi of the z value. Go back into like a few months ago. So the z value is 110. This is here. So that's 110 minus mu 109 divided by square root of 90. Okay, that's sigma. Remember that? So that was the phi of this thing, and I calculated that, and that is 0.5419. So this one, which is P of theta bigger than 110, that's the complement. So that is in fact 1 minus this, approximately 1 minus this 0.5419. Okay, so that is 0.458. Okay, so I have these two probabilities. By looking at this, you can say that I think I can accept that H0. I can accept that the mean is basically less than 110, less than or equal to 110. But you can also find that ratio, which is called, remember that was like the factor k, basis factor. So that is, k is 0.5419 divided by 0.4581, which is, I calculated that is about 1.18. So yeah, if it were around 2, for example, that would be much better, and even bigger than that. But that's okay. I mean, we have like some slight evidence, we can say, to accept H0, that the mean is in fact less than or equal to 110. And as I said, this might have some implications because the doctor should prescribe something. So and he has to decide whether to do that. And well, when it comes to decisions like that, don't expect anything being like 0 and 1. In fact, the decisions are like that. You make some decision, and it might completely go wrong. But when you base your decision on something like this, for example, then you are more confident, and in fact, in experience shows that this it is a more effective and more, say, sound, say, method than just things that based on your, say, gut, for example, gut feeling or something. So yeah. So based on this, we can say that there's slight evidence that, in fact, to accept H0. Okay, so that's how this thing works. There are things that you might say. One of them is, why did I choose this? This one, that X is normal, blah blah, that you have no other option. I mean, you have to choose something. You have to choose some distribution for that X. As I said, even the other method, the frequentist method, also chooses that X. I mean, chooses distribution for that X. But then it's this one. What is it? I erased that. It is the prior distribution for the parameter theta. And that's your belief. So you say, okay, I think it is this. And based on your belief, you continue doing certain things. But when you make some assumption, like that prior distribution, you collect data. So based on your data, you are changing that. So that's in fact where the posterior distribution comes into the picture. So you correct your assumption by using data collected, and then that posterior becomes now your starting point. And using that posterior distribution, you calculate these two probabilities, and using these two probabilities, and then compare them. So that was also, maybe in more sophisticated ways, we can say that say prior distribution that we select is some kind of measure of something. So yeah, it is different. The measure it shows my belief, but it also makes sense. For example, this one, or also mathematically it makes sense, because if this is normal, mathematically the posterior distribution becomes normal. So it might even be that people say, okay, why should I choose something which doesn't give me something nice here? Anyway, so that was the story of this. I will give you more examples next time on this, the test of hypothesis. So